Math 287, Cuesta College. I'm Joe Vasta, and today we're going to cover 5.1, inner product spaces. So before we get to that, I've got two vectors in R3, and I'm going to do something that we really officially didn't do in this class, and that is the dot product. So what is the dot product? We're going to go over that. And then this right here, whatever that means. We're going to find the angle between these two vectors, and then we're asking if they're orthogonal, and we'll talk about what that means as well. So this should be a review for most of you, and maybe you can pause the video and see how many of these things you can do if dot product is familiar. So what the dot product is between two vectors is a number that's associated with the two vectors. Okay, so it's kind of like a multiplication. You know, we don't have vector multiplication. We have scalar multiplication, but not where you put two vectors down. The result of this will be a scalar, and this is what you do. You multiply the first components together. So if you've never seen this, I'll write it down. So 1 times -2, and then we add, and we multiply the second components. So this is 4 times 2, and then plus, and then we multiply the third components. This is 2 times 3. So this gives me -2 plus 8 plus 6. You add that up, you end up getting 12. So 12 is the dot product of A and B. Okay, so now this right here, so why don't I label this? This is dot product. I do understand there is a cross product, and we're not covering the cross product. We're just covering the dot product. This right here is the length of vector A. The formula for the length of vector A is really the square root of A dotted with itself. Okay. So A dotted with itself, I'm going to multiply 1 times 1, which gives me 1. And then plus 4 times 4, which gives me 16, plus a 2 times 2, which gives me 4. And we could have said 1 squared plus 4 squared plus 2 squared. That's the same thing when you're dotting a vector with itself. So this gives me the square root of 21. This is called the magnitude. It has another name, the length, or you can call it the norm. And so that's how you find the length of a vector in R3. And also, this applies to R2 and R17. Okay, now what we're going to do is we are going to find the angle between A and B. So how are we to find the angle between A and B? Well, when it comes to angles, things like that, you know trig is going to come into play. And so we have a formula that says this: A dot B equals length A times length B times the cosine of theta. And this is for theta being in between 0 and 180. You see, if you got two vectors and they have an angle of like 180, that's great. But once it's more than 180, then what you've got is you're really measuring the smaller angle between those two vectors. So that's why the angles between 0 and 180, or 0 and pi, as we call it. Now, some teachers will say we're going to define the dot product, and when they first put the dot product on the board, they say this is the definition. Okay, that's cute, but I like doing it this way, saying the dot product is what it was, and then proving this. And so I'm not actually going to write out the proof. I'll include this in the PDF. This is the proof of the cosine formula, and it starts off with the law of cosines. And it goes like that. So I'll include this in the PDFs. We just have to know how to use this. A dot B. Well, we already did that. That's 12. And then we have this equals length A, root 21. Length B. Well, we have not done the length of B. It's going to be the square root of, well, let's see, 4 plus 4 plus 9. Well, 4 plus 4 plus 9 is 17. Then we have the cosine theta. And that theta is what we're trying to solve for. But before we do that, we're going to solve for cosine theta. So cosine theta, I'm kind of rearranging the equation as well. I'm going to divide both sides by root 21, root 17, so this is 12 over root 21, root 17. And this may be the first time you actually have to use a calculator in this class, because you're going to hit the cosine inverse. I'm going to look for this answer in degrees, so put your calculator in degrees, and I will round to the nearest degree. So when I punched this into my calculator, I got theta was approximately 51 degrees. So find the angle between A and B. It's about 51 degrees. Okay. Are A and B orthogonal? Well, in terms of what we're doing here, what orthogonal is going to be, it's going to be 90 degrees, or perpendicular. But this word has a more general meaning. But for now, for this example, are these guys 90 degrees? And the answer is no, they're 51. So we say orthogonal, we don't say orthogonal. People will spot you really quickly as a math fraud if you say orthogonal. So you want to say orthogonal. Also know that the dot product is a compatibility index. How compatible are these two vectors? Well, if it's positive, it means they have a chance, which means they have some of the same interests, you know. And what does that mean? They're kind of heading in the same direction. They're 51 degrees apart. So when the compatibility index of the dot product is positive, you are kind of almost going the same direction. Now when the dot product is negative, then we're in trouble. Then we're more than 90 degrees. And you can see that from this formula. So, you know, if you had a dot product of like negative 13, then one vector is going toward the ocean and the other one's going toward the mountains. So that's how I look at the dot product, as a compatibility index. And if the dot product was 0, in this example, we'd have the cosine theta equals 0. And that happens at 90 degrees. Happens at pi over 2. Okay, so then we would have said yes if the dot product was 0. So when the dot product is 0, then they are 90 degrees apart. They're kind of compatible. So there it is, a little review of dot product. And why did we go through all of this? because what we're going to do is we're going to generalize the dot product to inner product spaces. So, for instance, remember in this class we talked about vector spaces. So vector spaces, and when you saw that word vector, you thought, I know what vector spaces are. They're these little arrows. I know what vectors are. And yes, but vector spaces are a generalization of like R2 or R3. Vector spaces could be matrices or polynomials or continuous functions. Well, we're going to do the same thing with inner product space. So inner product space is a generalization of the dot product. So the dot product, we think we know the dot product, and we do, but inner product space is, an inner product is going to generalize the dot product. So let's see if we can do that. Trying to find the definition. I think we need some definitions here. Okay, so we'll take this away. Okay, let U, V, and W be vectors in a vector space V, and R is a scalar in F. Okay, we'll just assume it's real. An inner product, so this is the generalization of dot product. Inner product on the vector space is a function that associates a real number, and this is the notation for the inner product. It has these triangular brackets, or these trackets. And that is why we did not use the trackets when writing just vectors, because we knew we were going to do inner products. So it associates a real number with each pair of vectors and satisfies the following axioms. The inner product of a vector with itself is always greater than or equal to 0. And think, if you're getting a little confused, think if you dot U with itself, it's always going to be greater than or equal to 0. Inner product is 0. Inner product of a vector and itself is 0 if and only if that vector is the 0 vector. The inner product is commutative. Okay. And so is the dot product. Dot product is just one example of this. If you're going to take an inner product of two vectors and you have a scalar out there, you can bring the scalar in to that first one. And that's one property. And then we have another one. We have U plus V. You're taking the inner product of that with W. It is the inner product UW plus the inner product VW. So these are four axioms that make an inner product. Now the dot product satisfies all these. So the dot product is an example of an inner product. And let's continue just a little more. I think we need to see some of this for the next definition. The next definition here is this. If V has an inner product, it is called an inner product space. Okay? So it's really a vector space that is given an inner product. And then we say, hey, that's an inner product space. Let's talk about a few things with the inner products. I'm not going to assign problems where we verify those four axioms again and again. The problems that I assign, they'll have just given you an inner product and they want you to do things with it. So let's take a look at the rest of the definitions for this section. Okay, so we know inner product space. That's kind of a weird thing. It's a vector space with an inner product. The norm or length of a vector in an inner product space is denoted by that, and it's really the square root of inner product U with itself. And that reminds us of the dot product. The angle between two non-zero vectors U and V is given by the cosine formula that we had. Now I wrote this a little differently. I think our cosine formula that I used, I actually had length U, length V times the cosine, so it doesn't matter how you write it. Where theta is between 0 and pi inclusively. So This is something we'll use. This is something we'll use. U and V are orthogonal if and only if their inner product is 0. Okay? So in terms of Rn, you'll go, oh, that's 90 degrees. But in terms of other vector spaces, it's not necessarily 90 degrees. It just says their inner product is 0, which could have other meanings as well. So the rest of 5.1 is just some examples. And so that is what I'm going to do. We're going to make sure that we can crank out an inner product. So let's do that. Now the dot product in Rn, or the dot product in R2, is the standard inner product for R2. What I'm going to do is I'm going to give you a non-standard inner product. Okay? So the vector space is R2. You've got two vectors, U and V, which I'm going to call A, B, and C, D. I'm going to define the inner product to be AC plus 2BD. Okay, so it almost looks like the dot product, except there's a 2 there. Now we can go verify the 4 axioms to make sure the 4 axioms are satisfied. They are. And so this is a non-standard inner product for R2. You really don't want to use this one in your physics class, or your physics teacher will say, well, what are you doing? But it is a legitimate inner product. And what we're asked to do in this problem is to find the inner product of these two vectors, 2, 3, and negative 3, 4. So now would be a good time to pause the video to see if you can do this on your own. It's not that challenging. Okay, let's go ahead and do this. Okay, so I'm using this as the rule, AC. So this is 2 times negative 3, and I'll write that out. 2 times negative 3 plus, and then we have 2, that's part of the rule there, and then BD. 3 times 4. Okay, so what do I have here? I have negative 6. And this is going to be plus 24, which gives me an 18. So the inner product of these two vectors is 18. This is non-standard. So we didn't take the dot product, we took an inner product that was given. Now, can we have a non-standard angle between these two vectors? Yes. And a non-standard length? Absolutely. But in this problem, they just asked to find the inner product. Let's go ahead, do the second problem, which involves something other than Rn. The vector space is M2, 2 by 2 matrices with real entries. And so what we're going to do now is we're going to define an inner product. I have these 2 matrices. So one inner product that we can define is where we multiply corresponding elements. So AE plus BF plus CG plus DH. So this actually is a standard inner product for M2. So this is one, when people are doing inner products, this is one that people go to when they're analyzing matrices. So there's 2 parts. We're supposed to find the inner product of A and B, which we're not given, and find the angle between A and B. So I better give us A and B. Okay, so this was my mistake. I didn't plan correctly. I don't have much room here. Let's put A right here. So A is 1, 2, 3, 4. And B is 4, 5, -6, 2. Okay, so this is part of the given. This is given. So let's find the inner product of A and B. So I'm going to do that right over here. Hopefully I have enough space. Okay, so 1 times 4 plus 2 times 5 plus 3 times -6 plus 4 times 2. So what does this give us? This gives us 4. These two matrices have an inner product of 4. Okay, let's go ahead and find the angle between A and B. Now, you know, when you're doing problems, you have to be given the inner product to know what to use, because we could have done a non-standard inner product for M2 and we could have thrown like a 3 in front of the AE and that would have been a non-standard inner product. So you have to know what the inner product is. Sometimes when they don't tell you in a math book, it defaults to the standard one. So we want to find the angle between A and B. And so this is when it gets a little crazy. We are finding the angle between two matrices. Yes, and that's what we're going to do. We're going to go ahead and use that formula. So I'm going to write up the formula here. Angle, let's see, let's just say inner product AB equals length A times length B times the cosine of theta. So we're going to have to use our calculator in this problem at the very end. Okay, inner product of AB, we already computed that. That is 4. Length A. Let me go ahead and do that off to the side, just in case you're a little confused with this. Well, if you look at your definition, the length of a vector, or the norm of a vector, is really the square root of the inner product of A and itself. So inner product A with itself, and here's A. It's going to be 1 times 1, see AE, and then 2 times 2, 3 times 3, 4 times 4. And then we're going to add all those together. So this is going to be 1 plus 4 plus 9 plus 16. So it looks like it's going to give me 30 under that root, so this is root 30. And so this guy right here can get replaced with root 30. In a similar fashion, we will find the length of B. It's going to be a square root of something as well. So let's see what this is going to give me. This gives me 16 plus 25 plus 36 plus 4. So if you add all that together, I think you get 81. And then this is the cosine of theta. So this is 4 equals 9 root 30 cosine theta. Cosine theta equals 4 divided by 9 root 30. If you're going to enter this all in on your calculator, you need parentheses on the bottom. Otherwise, the order of operations will say 4 divided by 9, and then it will multiply 4 nines times root 30. So you need parentheses down there. You have to hit your inverse cosine button and make sure your calculator is set on degrees. I'm going to round this to the nearest degree. And so what I got for an answer on this was approximately 85 degrees. So we've just found the angle between these two matrices, these two vectors, and you can do this only when you have an inner product. So if you just had a regular vector space without an inner product, then this would be meaningless. And so would the asking for an inner product if you weren't given one. So this is given the standard inner product for matrices, for 2 by 2 matrices, and we get 85 for our answer. Let's go ahead and do one more kind of example, and you'll see that 5.1 hopefully will not be that lengthy when it comes to homework. Let's go ahead and do problem number 3. Okay, your vector space is C, and then there's a 0 up there. Here's an interval from 0 to 1. So what this means is continuous functions on that interval. If it had said C1, then you'd have continuous functions and their derivatives are continuous as well. And C5, the first 5 derivatives. Okay, but we have this here. And we have inner product of f and g is integral from 0 to 1. It kind of sweeps out that interval there. F of g, well, sorry, f of x, g of x, dx. What I'm noticing is I forgot to give an f and a g on this problem where I'm asking you to find the inner product between f and g. Okay, so let's let f of x equal x and g of x equal x squared. Okay, so that's what we're going to find the inner product of. So here it is. F, G, and maybe you want to pause the video and see if you can find the inner product of those two functions. And not only that, maybe you can find the angle between those two functions, of those two vectors. So here it goes. The inner product of f and g, we are going to take the integral from 0 to 1. I'm following this rule up here. I multiply those functions together. So x times x squared is x cubed. So you take the antiderivative, you get x to the 4th over 4. This gets evaluated from 0 to 1. You put 1 in there, that's 1/4. You put 0 in there, that's 0. So we have just found the inner product. The inner product is 1/4. So the inner product is a generalization of the dot product. Okay, so I'm not saying we're doing the dot product here. I'm saying the dot product is one example of an inner product. 1/4. Find the angle between f and g. Okay, so to find the angle between f and g, we're going to go like this. Here's f and g. Length of f. Then this is length of g, cosine theta. Okay, so it might be I don't have enough room on this piece of paper. I think I'll have enough room. Maybe do some work over here. And so, inner product of f and g, and we're talking the same f and g here. That's 1/4. Okay, length f. Well, what the length is this. It's the square root of the inner product of f with itself. Okay, so f looks like x. So if I go x times x, that's x squared. Of course, there's a square root there. And then what do we have? We have x cubed over 3, evaluated from 0 to 1, is going to be 1/3. So we have that right there. Or if you like, 1 over root 3. Let's do the same thing with g. Why? Because we have that right there. So this is the square root of the inner product with g with itself. So g is x squared. So x squared times x squared is x to the 4th. So this is integral from 0 to 1, x to the 4th dx. We're taking the square root of that. Well, the integral of x to the 4th is x to the 5th over 5. Evaluate it from 0 to 1. 0 is going to 0 out, and you put 1 in there, you get 1/5. Of course, this is the square root of 1/5, which is 1 over the square root of 5. Wow, so we have 1 over root 3, 1 over root 5, then we have cosine theta. So the cosine of theta actually equals, I'm just going to multiply those together, this is going to be the square root of 15 over 4. In which then you will use your inverse cosine button on the calculator, making sure your calculator is in degrees, and figure out what theta is by pushing some buttons. I'm going to round to the nearest degree. What I ended up getting is theta is approximately 14 degrees. And so that concludes section 5.1. The next section is 5.2.